So in this video, I'm going to be deriving the time-dependent material and energy balance equations for this situation here. And they will end up being differential equations that we will end up coding into Python and solving with the solve IVP function. I'm going to start off by just drawing a little diagram of the situation we have. So we have the tank here with the jacket, and then the coolant around that. And what we are going to start with is the Arrhenius equation, which is just K, the reaction rate, equals A times E to the negative and the activation energy over R times the temperature. And what is different about our situation here is that instead of this being A like the normal Arrhenius equation, it is given to us as K naught. So next, in the tank, we know that there is a first order reaction going from A to B. So we can write that reaction rate equation for R as just K, a rate constant from the Arrhenius equation, times the concentration of A. So as you can notice in the problem, it gives us our E over R as 8,750 Kelvin. So I can plug that in here. So we will get negative 8,750 over T there, instead of having just our activation energy over R. And then now we just need one final equation before we can start writing our differential equations. And this equation is going to be finding the amount of heat transferred, the amount of heat transferred from the reactor to the coolant. And that is going to equal our UA value here. UA times the temperature of the reactor, obviously, minus the temperature of the coolant. So now we can find the differential equation for the concentration of A over time. So I'm going to denote that as dCA over dt. And how we're going to do this is by doing a mass balance, where we're just going to use the normal equation where the accumulation equals what goes in minus what comes out. And then also, since we have a reaction going on here and some of A will be consumed, it is also minus what is consumed. So for this situation, we're going to want this all in mass, obviously. So this is going to start off as our concentration, which is mole per liter. And then times, this will be 1 over the time in seconds or whatever. And then to get this just in our mass, which is moles for this situation, we're going to need to multiply by volume to get these to cancel, as you can see there. So that means that we have to multiply this by the volume, and that'll be the left-hand side of our equation. And then now, we need to figure out what is going in, so that'll be our flow rate in, Q, and it will actually be the same flowing out, because it doesn't say it's changing in our problem. So that'll mean we can just put the Q there and multiply by both our concentration going in minus our concentration out, which will just be Ca. And then finally, we just need to subtract by what is consumed, which that'll equal our rate constant, K, times the concentration of A. But again, these units need to be in mass for our mass balance. So K is usually given in molarity over time, which would just be moles over seconds time liters. So we're going to again need to multiply by the volume in order to get these to cancel. So again, we're going to multiply by the volume right here. And now, just to simplify this a bit, we can divide everything by the volume, and we will get our differential equation of dCA over dt will equal Q over V times Q over V times CA in minus CA minus KCA. So now we can work on finding the differential equation for the change in temperature, which we will be doing an energy balance for. So to start off, we're going to need the equation for enthalpy, which is delta H equals mass times C, the specific heat, times change in temperature. So to start off, we're going to be using the same thing, where the accumulation equals in minus out minus what is consumed. So we can start off by getting our H accumulated, which will be the mass, which we're going to use the density times the volume for the mass. And our C is given in the problem right here, so that'll again just be C. And then times our differential of the temperature over time. And that will equal our Hn minus H out, and then minus our consumed, which will be just our heat that is transferred from our reactor to the coolant right here, which I'm just going to call HT for H transferred. So I forgot to mention, in this equation we are going to just have some heat release because of the exothermic reaction as well. And then now we can start substituting in for these individual H's on this side of the equation. So I'm just going to copy this down again. So we have space. So to substitute in for the Hn and H out, we're going to get the mass by multiplying the density again by the flow rate, and then again we'll be multiplying by C, and then it will be the temperature in minus the temperature out. And the temperature out will actually be equal to the temperature in the reactor, just like the concentrations. So this will just be T right here. So now we can do the heat transfer part of this equation, and it actually will be the exact thing that we calculated here for the heat transferred from the reactor to the coolant. So we will be subtracting that. U is T minus Tc. And then for this heat that is released from the exothermic reaction, actually made a mistake, and it will be added instead of subtracted. Finally, we will be adding the heat released from the exothermic reaction and again we will be multiplying that by the rate of the reaction and the volume, and then the concentration of it. And now finally, just to simplify this whole thing, we want to get the dt over t over dt on its own side, so we can divide everything by this. So our final differential equation will just be dt over dt equals q over v Tn minus T minus UA over density times volume times C T minus Tc, and then plus negative delta H R times K times concentration of all over the density of C. So these will be our two differential equations that we will be inputting into Python in the next part of this video.